Hello everyone, I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to explain chemical reactions of phenol. This is the part 1 of chemical reactions. Since phenols are the important class of organic compounds and generally they participate in all type of organic reactions. Some of the chemical reactions of phenols we are going to discuss in the first lecture, part 1. First reaction of phenol is acylation of phenol. Acylation of phenols means replacement of phenolic hydrogen by RCO group or acyl group. As in the case of alcohol, in the case of alcohols, the process of acidification is the reaction of alcohol with carboxylic acid in the presence of acid or base. But in case of phenols, direct acidification of phenols does not take place. With phenols, esters are formed by the reaction with acid chlorides or acid anhydrides in the presence of alkali or strong base. Which reagent we are using for the acylation reactions? On this basis, acylation reaction can be divided into two classes. First is the acetylation, when phenolic hydrogen is replaced by acetyl group CH3CO. When phenolic hydrogen is replaced by CH3CO group, for this acetyl chloride or acetic anhydride can be used. This reaction is known as acetylation. Reaction of phenol with acetyl chloride in the presence of alkali, product will be phenyl acetate. If we want to prepare aromatic esters, for this reaction of phenol is carried with the benzoyl chloride C6H5COCl in the presence of NaOH and phenyl benzoate is formed. This reaction is very important in organic reactions since it is used for the detection of the phenols. This reaction is known as Schotten-Baumann reaction. One type of rearrangement that is involved in the acetylation or related with the acetylation reaction is Fries rearrangement. In Fries rearrangement, an aryl ester is transformed into hydroxyaryl ketone in the presence of Lewis acid and an aqueous acid. An acyl group belonging to the phenolic ester migrates to the aryl ring. That means this acyl group, which is the part of the this acyl group which comes from the acetyl chloride, this acetyl group will migrate to the aromatic carbon. This type of rearrangement is involved in the Fries rearrangement. And Fries rearrangement is ortho and para selective. Since OH or phenolic OH is ortho para directing, so the rearrangement involves ortho or para position. The acyl group attaches itself at the ortho or para position of the ring. Selectivity of the reaction can be directed by modifying the reaction conditions. That means which product will be formed as the major product, ortho substituted or para substituted, such as the temperature under which the reaction is conducted or the solvent. By changing the temperature or by changing the polarity of the solvent, we can control the formation of ortho and para product. Low reaction temperature and polar solvent favors the substitution at para position, whereas high temperature and non-polar solvent favor ortho position. Mechanism of Fries rearrangement. The mechanism of Fries rearrangement, the carbonyl oxygen belonging to the acyl group forms a complex with the catalyst, that is AlCl3. The formation of the complex with the carbonyl oxygen is favored over the complexation of the phenolic oxygen, since the carbonyl oxygen is richer in electron. and is therefore act as a better Lewis base. The bond between the phenolic oxygen and the acyl complex, this one, phenolic oxygen and the acyl complex becomes polarized, resulting in the rearrangement of AlCl3. This steps involves the rearrangement of AlCl3 bond to the phenolic oxygen. This results in the generation of acylium carbocation. This RCO group is removed from here and in the form of carbocation. The acylium carbocation goes, since it is carbocation, it will attack on the electron rich position, that is ortho or para. So acylium carbocation goes on to attack the aromatic ring via electrophilic aromatic substitution reaction that generally takes place on ortho and para position. Second reaction. Second reaction is alkylation of phenol, or it is also known as Williamson's synthesis. In acylation reaction, phenolic hydrogen is replaced by acyl group. In alkylation reaction, phenolic hydrogen is replaced by alkyl group. In the presence of a base such as potassium bicarbonate and heat, phenol reacts with alkyl halide to form an ether, phenolic ether or aromatic ether. For example, reaction of phenol with ethyl iodide in the presence of aqueous NaOH, and there is the formation of phenyl ethyl ether. Mechanism of alkylation. In the first step, the base, that is potassium carbonate or any alkali, the base deprotonates or removes the proton from the hydroxyl group, creating or converting into the phenoxide ion. This ion can undergo a substitution reaction since it is negatively charged, or it act as nucleophile. It will attack on the carbon that is directly attached to the halogen, that is always partially positively charged. So nucleophilic nucleophilic phenoxide ion attack on the electrophilic carbon of 1-chloropropane, and there is the formation of ethyl phenyl ether. That is simple mechanism. In the first step, there is the formation of phenoxide ion, and in the second step, phenoxide ion attacks on the electron deficient carbon directly attached to the halogen. Again, ethers involved one type of rearrangement, that is Claisen rearrangement. In Claisen rearrangement, carbon-carbon bond forming reaction. This is thermal rearrangement of phenolic allyl ether. That means alkylation is with the allyl chloride. When orthoallyl ether of phenol is heated to about 200 degree centrifuge temperature, it rearranges into orthoallyl phenol. That means allyl group migrates towards the ortho position of the phenol. It has been observed in this reaction, the allyl group migrates almost invariable to the ortho position unless the ortho positions are blocked. There is an inversion of the allyl group during the rearrangement. That means the allyl group, allylic carbon that is attached to the oxygen will not remain attached to the carbon atom of the allyl group, which get attached to the aromatic nucleus, is not the one which is attached to the oxygen atom of the ether. Here you can see this carbon is attached to the phenolic oxygen, and after the rearrangement, this carbon will not attaches to the ortho position, whereas this is carbon highlighted by the star, this carbon is going to attach with the ortho position. Rearrangement of mixture of allyl phenyl ether do not give products, shows rearrangement is truly intramolecular. Do not give cross products, so it shows the rearrangement is truly intramolecular. When both the ortho positions of phenyl ethers are blocked, the allyl group migrates to the para position. Here you can see both the ortho positions are blocked by CH3 groups, then Claisen product will formed at the by the migration of the allyl group on para position. This is the mechanism. The cyclic mechanism account for the intramolecular rearrangement of allyl ether to ortho-allyl phenol. This cyclic transition state is formed, and after that it is converted into ortho-allyl phenol. Next reaction is reaction with aqueous ferric chloride solution. This reaction is also used for the detection of phenolic group in organic mixture. Phenol reacts with aqueous neutral ferric chloride, forms ferric phenoxide complex. This is ferric phenoxide complex, which is violet colored. This reaction is used to distinguish phenols from alcohols. Compounds with a phenol group will form a blue, violet, purple, green or red brown color upon addition of aqueous ferric chloride. Depending on the different carbon skeleton of the phenol, whether it is simple phenol, cresol, resorcinol or hydroquinone, on this basis the phenols can produce blue, violet, purple, green or reddish brown color with of aqueous ferric chloride, and the same type of complex ferric phenoxide complex will form. Next reaction is Buchra reaction. In this reaction, phenolic group is replaced by amino group by the reaction with aqueous ammonium bisulfite in the presence of ammonia. For example, reaction of beta-naphthol. Beta-naphthol react with ammonium bisulfite in the presence of ammonia and form beta-naphthylamine. Next is the coupling reaction. Coupling reaction is also a very important reaction of organic reaction. Compounds which contain strong electron donating groups like hydroxy groups can activate the ortho and para position. On a benzene ring can undergo coupling reaction with a diazonium ion. A coupling reaction is one in which two aryl rings are joined by an azo group. Azo group is nitrogen double bond nitrogen group. This coupling reaction usually occurs at para position of the phenol. This is benzene diazonium chloride. Benzene diazonium chloride is formed by the reaction of, as we discussed in the last lecture, benzene diazonium chloride is formed by the reaction of primary aromatic amine with sodium nitrite and concentrated HCl at lower temperature. It is converted into benzene diazonium chloride. When benzene diazonium chloride in alkaline medium react with phenols or naphthols, it forms a coupling product or diazo product or a colored compound. This is the mechanism of coupling reaction. Benzene diazonium ion react with phenol. Hydrogen attached to the para position of the phenol. In the first step, it forms adduct, and after that, it is converted into diazo compound. Next reaction is reaction with phenyl isocyanate. By the reaction of phenol and phenyl isocyanate, diphenylurethane is formed, which is a colorless crystalline compound and used for the detection of phenol, diphenylurethane, by the reaction of phenol and phenyl isocyanate in the presence of aluminium trichloride and chloroform solvent at 26 to 58 degrees centigrade. Diphenylurethane will form. Next reaction is reduction of phenol. Reduction of phenol, that means addition of hydrogen or removal of oxygen. Phenol is reduced in the presence of nickel at high temperature into cyclohexanol. Cyclohexanol is used as a solvent in rubber industry. This was all about the first part of chemical reactions of phenol. In the next lecture, we will discuss some more reactions of the more important reactions of the phenol. Thank you. Stay safe.